Hello, linear algebra students. Continuing proof that a subset can satisfy all the properties of the vector space. Instead of just kind of taking a pass on it like the book does, where they make it a definition, we're going to use exercises 28, 29 in section 4.1 and finally prove that our theorem 1 is true. Now the book has as theorem 1 something we're going to prove soon, next video, using the word span. We need to get to the word linear combination first for a number of reasons, but let's finish this off. Okay. All right, so additive opposite, you get the zero vector. That's an axiom. You know which one that is. Now, as, let's see, as this is equal to that by, okay, what do we do from this side of the equation to that one? Oh, we're using the fact that we have a different kind of distribution. Which axiom is that? Not one we've used lately. Of course, 1 in the field plus its additive opposite is equal to 0 in the field. That's a field axiom. And 0 in the field times v, what we know from, oh yeah, by problem, I'm sorry, which one? That's equal to 0 vector. So we have that v plus -1 in the field multiplied by v is equal to the 0 vector. Take this equation and flip it over. That's called using the fact that equality is symmetric. Okay, so you just flop that over. Now you've got that the 0 vector is equal to that over there. Okay, why did I do that? Well, I want to add something to both sides. What am I adding to both sides? The additive opposite of v. Okay, that's just algebra. And what have I done from here to here? This is the same, just different colored ink. From here to here, I'm regrouping, so that's axiom. You fill in the blank. A vector plus its additive opposite is equal to 0 vector. I guess I've asked you that too many times, so I didn't ask you to do it again. What axiom that is. And therefore we have this statement that follows from this one. And why is this this? Oh, because I just add the 0 vector. And so that doesn't change the thing. That's axiom, you fill in the blank. Well, this statement is exactly what we wanted to prove. That the additive opposite of a vector is the same thing as -1 from the field scalar multiplied by the vector. QED, quod est demonstratum. Alrighty, so now we are ready to move along to our conclusion of theorem 1, which you can see, we're starting there. And I'm hoping you can see there's not too much glare on the important bits. Okay, good. All right. So remember what our theorem 1 is. The book is just calling it a definition. They're not calling that theorem 1 because they're not proving that a subset which only satisfies a few properties is also a vector space. They're implying that they're proving it by sending the reader to problems, exercises 25 through 29, but they're not actually doing it. So you and I have done it, right? Well, we're just about to finish it off. So just using these 4 premises. Now, premises are those preconditions in which before you can say something's true, right? Wasn't it just 3 preconditions last video or in the book? They're saying that, and I fell into that trap again, but there's actually 4 things you need to check. You have to check that, first of all, that thing you're about to prove is a vector space is a subset of a vector space. You have to prove that the 0 vector is in that particular subset of that vector space. That for any 2 vectors in that subset, their vector sum lands back in the subset. We're going to go, in the next video, we're going to go examples of subsets of R2 where that does not happen. And so that's why how you prove something's not a subspace sometimes. Or that for all scalars in the field is exactly the same. It's not a subset of itself. For all scalars in the field and for any vector in the set S, that scalar multiple of that vector also stays within S. And when that's not true, you can prove something's not a subspace. Again, we're going to be doing that next video, a bunch of examples. So using those 4 only instead of all 10, we'll be able to say something S is a vector space in its own right. If we get this one thing done, because if you remember, we had all 10 axioms satisfied except for axiom 5, which would be this in this context, that for any vector in S, its additive inverse is also in S. That one, we didn't have a guarantee on that. That's why we went through problems 25 through 29. Okay? You'll be able to prove it is true from those 10 axioms. So here's the finish. take any arbitrary vector in S. When you're trying to prove a statement is true about any old vector, this is a way of phrasing it mathematically. Let an arbitrary vector in the set under question be chosen. So I don't care which one you choose, I'm going to be able to make these assertions about it and proving it. Since the opposite of 1f is a scalar in the field, then by premise 4 up here, which we get to assume, that's in the premise, we're going to have that negative 1f times that arbitrarily chosen vector v is an S. Okay, that's our premise that you show these 4 premises, you have this up, so we get to assume these guys. By problem 29 in section 4.1, negative 1 times negative 1 from the field times the vector, scalar multiplied by the vector, is equal to the additive inverse of that vector. Therefore, for all vectors in S, its additive inverse is also in S, right? This is equal to that, and that is in there. So this is in there. Therefore, a subset satisfying these 4 premises only is itself a vector space. Oh, sorry. Camera work, my bad. Okay, let's see where did I leave you off. Okay, since any scalar, not any scalar, since the scalar, the opposite of 1 in the field, has to be in the field by conditions of a field, by our premise 4, that scalar in particular times our arbitrary vector has to be an S. Okay, so we've got that this has to be an S, but by problem 29, this is the same thing as that. Therefore, the opposite of V is also an S. Bada boom, bada bing, we're done. We have that now S with that same vector addition and that same 0 vector from V, which we asserted had to be in there, using the same field, the whole field, scalar multiplication went up, it in itself is a vector space. Okay, now, this is glorious moment, right? Glorious moment, but guess what? It gets even better. If you just get used to the definition of the phrase linear combination, we can get these 4 steps down to 2. So that's a plug for the next video where we talk about linear combinations, the definition of the word linear combination, the definition of the word span. Very helpful, and that'll help us get to the book's theorem 1 in section 4.1. Next video.